Here we are. This is section 8.2, and this is on inverses of relations. This is a really important section that you will use the rest of your mathematical career because we do deal with inverses a lot in math. The goal of this is to explore the definition and to figure out that inverses of a function are not always a function themselves. Okay? Here's a journal choice, and you may do that if it interests you. We're going to look at the book for an example here. Let's look at it up here. I don't know. I'm not much into science stuff, but I do think that this is worth discussing. There we are. Okay, in 1929, astronomers, I think that's Hubble. I don't know what that is. Humason, I don't know. I'm just making that up. But they have cool first names, Edwin and Milton. They kind of figured out that our other galaxies are moving away from our galaxy. Receding. You guys know what that word is, receding hairline. Okay. The relationship between distance and recession speed is given at this table below. Distance is given in megaparsecs. I don't know. Parsecs. I don't know. But anyway, one of those is 3.26 million light years, which I think is, I guess, far. Speed is given in kilometers per second. Okay, so while I don't really have a good visual of what's happening here, basically, in a nutshell, our galaxies are moving away from each other, and this is the speed. Okay, I would guess that sometimes distance is going to be easier for them to measure, and maybe sometimes speed is, I guess you'd have to have a really good motion detector. But in this table, the left column has values of the domain x, and the right column has values of the range variable y. The function that maps distance onto recession is called Hubble's law, and it is this equation. So they know this relationship, and this is the equation for Hubble's law, and I have heard of that before, I think. Astronomers use Hubble's law to estimate the distance to a galaxy based on its apparent recession speed. So apparently sometimes it is easier to measure that speed, and it's measured by shifts in the spectrum of light. Okay. In other words, the speed becomes the domain variable x, and the distance becomes the range variable y. So apparently, sometimes it is easier to notice what the speed is instead of the distance. So sometimes we want to switch the table so that the speed is the domain, what we get to choose, and the distance is what is the output. They won't have the same equation, obviously, because the relationship's not the same. But these two equations are related. Okay, and how they're related is they took the x and the y and they switched them, and then we always get y by itself, so they have y equals x over 70. These are called inverse of each other. Okay, so here's the new table, and if you notice 0, 350, 700, oh my gosh, didn't mean to go that fast. 0, 350, 700. They just switched the tables, but that is modeled by that equation they gave you. Okay. So basically, in a nutshell, what an inverse is the relationship between variables if you switch the x and y. Okay, and it is helpful because sometimes the data that you have available to plug in is not what is modeled by the table, if that makes sense. Sometimes you have the speed handy, sometimes you have the distance handy. So sometimes it is helpful to look at these tables in an inverted way. Okay, so this is the example. You have seen the word inverses a lot in math before. There's been additive inverse, inverse variation, inverse of matrix. There's lots of different meanings here, but definitely a relationship is involved. Here is the formal definition of inverse of relation. Basically, all you do is switch the x and y's, okay? It can be a function or it doesn't have to be a function. This is very easy to do. So what is the inverse of q? So you can write q inverse like this. Equals forehead, nose, and chin. What are the ordered pairs now? We'll just switch the x and y. 5, -2, 7, -1, 3, 0, 7, 1, and 1, 2. Okay, if I was to graph both sets, which is going to be a little bit sloppy because I don't have graph paper right here. Let's graph q first. I'm going to do that, actually. I'll do Q in blue. Okay. -2, 5. 7, -1. 0, 3. 1, 7, and 2, 1. Okay, that's blue. Now I'm going to do this Q inverse in that brick red color. 5, negative 2. Lost my count. 7, negative 1. Oh, this one I did wrong. Negative 2, 5, 7. See, I went down here. That should not be blue. I'll go over this one. Was that bothering you guys when I did that? That probably drove you nuts. Negative 1, 7. It should have been up there. Okay, is that better? Sorry. 3, 0. And 7, 1. Oh yeah, that's better. And 1, 2. Okay. Can you see that they are related? Do you see anything that they have in common? And you should notice that I could draw a full line right here, and I could reflect these points and they would map on top of each other. Okay? They are related. They are reflection images of each other over the line y equals x, which makes sense because we switched the x and y. So if I were to graph them, shouldn't their coordinates flip over that line? The answer is yes. Okay. I shouldn't have to tell you then domain and range. How would they be related? Well, what did I do to go from one to the other? I took the x's, which is usually your domain, and I switched them with the y's. So how are domain and range related? Well, one function's domain is the other's range, and vice versa. Okay? I do think you'll want to write this down. This is the big one. The domain of G is the range of F, and the range of G is the domain of F. If F is a relation and G is its inverse. It says relation, notice not function, okay? Because this works for anything. And if a rule for F exists, you can also find the rule for Y, or G, excuse me, by switching the X and Y. And then you can figure out what that relationship is, just like they did for Hubble's law, okay? And the last thing is the graph is a reflection over that line Y equals X. So do jot that down. How can you find an inverse if you're dealing with the equation? It's very easy. All you do is switch the x and y and solve for y. It should be very common sense now that we know what the definition of inverse is to switch the x and y, because that's what an inverse is. It just switches the x and y. And the reason we end up solving for y is because that's how we're used to expressing things. That's how we can find a good rule, okay? So consider the function y equals negative 2x squared with its domain as a set of all real numbers. What is the equation for the inverse of this function? Okay. We're going to switch x and y. So now I have x equals negative 2y squared. And we're going to solve for y. And this is where it gets a little bit tricky. I divide both sides by negative 2. Okay, so I have y squared equals negative 1/2 x, or you could put negative x over 2, also fine. I'm going to square root both sides. When I square root both sides, usually when we square root a variable like this, we do throw the plus and minus in front. It is imperative that you do that here, okay? The reason being is because there's two sets of values that you could square to get this negative 1/2 x, and you need to consider both of those, the positive and the negative. So my new equation is y equals plus or minus square root of negative x over 2, or negative 1/2 x. How do I type that into my graphing calculator? You have to do it as two separate equations. You can't do this x plus or minus thing. So we put y equals square root, parentheses, negative x over 2, and you would graph that. And then y equals, throw the negative in front, square root, negative x over 2. Okay, so let's look at it. They want us to graph the function and its inverse. So I did not pull up my calculator, so hold on one second. Okay, let's look here. Y equals negative 2x squared was the original. Okay. And then we had tab. Y equals, we want, oops, nope, square root. So, you guys will be faster than me at this. Is it under, where are all those math tools at? This is when I need you guys. Oh, well, I found square root. Let's just hope we don't have to do anything more difficult than square root. So I don't want that. Control, oops, get away from me, menu, I don't want you anymore. How do I get off of there? Okay, square root, control this, and then I need parentheses. Is it negative x over 2? I don't even remember anymore. Enter. There's one. And I need to do one more. So tab. Now I need to do negative square root parentheses negative x divided by 2. And this is probably painfully slow for you to watch, and I apologize. And that is the same thing we just did. It looks like. Did I graph it? Let's go up there. That doesn't. Oh, I did negative, negative. See, why don't you guys tell me this? Enter. There it is. Okay, so there's the inverse, and it's both pieces because that inverse does have two pieces because of the plus or minus thing. Okay, the question then was, is the inverse a function, why or why not? What do you guys remember about functions? Is a sideways parabola a function? And your answer should be no. It fails the vertical line test for one, and there could be two outputs when you plug something in because there are two separate equations here. When I plug x in, I have to do it this way and that way. So it is not a function, but that's okay. It's still its inverse. Okay? So how do we determine if a relation is a function? We check the x and vertical line test. We did this in chapter 1. Okay? How do we determine then if a relation's inverse is a function? Well, this should make sense. Instead of checking the x, we should just check the y, because when you do the inverse, those columns are switched. So you would check the y, and instead of a vertical line test, you could do a horizontal line test. Okay? This is if you are actually given the graph of an original. Now, if you are told to find the inverse, like we just were, it's sometimes easier just to actually figure out the inverse is, and then just check it like you did before. The x's are vertical line tests. Okay, in the first two examples, are the inverses functions? Well, let's go over here. I thought we only did one example. Alright, on this one, the relation itself, negative 2, 1, 0, 1, 2, is a function, and it would pass the vertical line test, but its inverse is not, because if you checked the y's here, you would notice 5, 7, 3, 7, there's 7. It showed up twice. Okay? Or you could have checked the horizontal lines if you were only graphing the original. Now, we went ahead and we actually found it, then you could have just checked the x's again. Okay? So those are your options. These two functions are graphed. Is the inverse of each function a function? Explain your reasoning. Well, we could actually plot the ordered pairs and see what it looks like, but instead, I'm just going to check the horizontal line test. It gets a little wishy-washy here. I can't quite tell, but I will tell you that I know stuff. If I zoomed in on this graph, it is like always going to be gradually going up. It looks like it's leveling off, and it is a little bit, but it is never quite get horizontal. So is inverse of this a function? Yes, the inverse is a function, and the original is a function. Passes that horizontal line test for the inverse check. This one, the relation is a function, but its inverse is not because of that location right there. So the inverse is not a function. And they want us to state the domain and range. Okay, the domain here, left to right, would I go forever? Yes, I would gradually go to the right forever and ever, and to the left. So the domain is all real numbers on the function. The range is also all real numbers because it will go up forever. The domain and range should switch for the inverse, so basically the domain is still all real numbers and the range is still all real numbers. Things will be different on this graph. The domain left to right still is going to be all real numbers because it will go to the right forever and the left forever. The range here, though, is not all real numbers. It does cap out here. 1, 2. The range was y had to be less than or equal to 2. So for the inverse, the domain and range switch. Now, domain is always talking about x though, so I won't put a y when I switch them. I will now say that x will be less than or equal to 2, and now the range will be all real numbers. If it's hard for you to see and you need to graph it, please do so. Quote of the day: life is like a circle. You are not on the top or the bottom forever, and you can leave this lesson now inspired. Okay, we will talk more about inverses tomorrow. If you're a little wishy-washy, it's not hard. The big things are switch the x and y's, and if you have an equation, you need to switch the x and y's and solve for y's. Okay, we'll look at it more tomorrow, and I hope you're now thoroughly inspired. Goodbye.